This resource is the 9th in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. Finding the roots of a function means to find the values of x which cause the function to equal 0. When we consider a quadratic function, we can use the quadratic formula to find these roots. But suppose we need to find the roots of a higher order equation. Unless the function is easily factored, finding these roots is nearly impossible. In small stretches, any function can be approximated by a line tangent to the function at some x value, which we will call x sub 0. Recall that the derivative is exactly the same as the slope of the tangent line. The equation of this tangent line in point-slope form is then y minus the function value at x sub 0 equal to the derivative at x sub 0 multiplied by the quantity x minus x sub 0. We will assume that this x sub 0 is our first guess for a root of the function, but we will be able to improve this guess. Since we want to find a root of the function, we want to find the x-intercepts for the function. Since the tangent line is a good approximation for the function, we will try to find the x-intercept of the tangent line. We call this x-intercept x sub 1, and we'll have a corresponding y value of 0. We have 0 minus the function at x sub 0 equal to the derivative at x sub 0 multiplied by the quantity x sub 1 minus x sub 0. Solving this equation for x sub 1, we get the quantity of the derivative multiplied by x sub 0 minus the function value divided by the derivative. Simplifying, we have x sub 1 equal to x sub 0 minus the function value at x sub 0 divided by the derivative at x sub 0. This formula sets up Newton's method for finding the roots of a function. Let's see an example. Suppose we want to find the roots of the function y equal to x cubed minus 6x plus 2. This function has no rational roots, but if we look at the graph, there is clearly a root somewhere between 2 and 3. We will attempt to use Newton's method to find a reasonably good approximation for this root. Since we will need it for the method, we start by finding the derivative of the function. Y prime is equal to 3x squared minus 6. Let's start with the assumption that 2 is a root for the function. We will use Newton's method to improve this guess. This improved guess, x sub 1, is equal to the initial guess minus the function at the initial guess divided by the derivative at the initial guess. Plugging in our initial guess of 2 into the function and its derivative, we get negative 2 and 6, respectively. Our improved guess will be 2 minus negative 2 divided by 6, which is exactly 2 and 1/3. This is approximately equal to 2.333. If we plug this amount into the function, we find the function value equal to 0.70026. So 2.333 is an improved guess for the root of our function. But we can do better if we use Newton's method again. What happens if we use Newton's method again, but with 2.333 as our initial guess? Again, we have the basic setup to improve our approximation for finding the root of the function. Plugging 2.333 into the function and its derivative, we get 0.70026 and 10.328667 respectively. Solving, we get a new guess of 2.265 for our root of the function. Plugging that into the function, we get 0.02996. Again, we are closer to 0, so our approximation has improved. Let's do one more iteration to improve even more. We had a guess of 2.265 for our root, and we look to use Newton's method to improve the accuracy of our guess. Plugging the value into the function and its derivative and solving, our next approximation for the root is 2.261. When we find the function value for 2.261, we get negative 0.00749. Again, our approximation has improved. So how do we know how many iterations of Newton's method we need to complete? It depends on how exact you want your approximation to be. Continue with additional iterations until your root is good enough.